Morning. Let's get started. Hi everyone. How's it going? Okay. Yeah. So the TAs are almost done grading the exam, so we hope to release them sometime today or tomorrow. And yeah, so the previous homework has also, or the next homework has also been released. So it's the same schedule as always, like 2 weeks. And yeah, other than that, there's a programming assignment. That's all that's going on right now. So today we're going to do sample sort. Last time we did Bitonic sort, which is this parallel sorting mechanism. If you remember, it does sorting networks. So you have these n wires, and through some clever set of comparisons, you eventually get to the right answer. And sample sort is actually it uses Bitonic sort, but I want to do sample sort because it's more practical. Because like we talked about last time, Bitonic sort does not reach the sorting lower bound. It's like sorting lower bound is n log n, but Bitonic sort is n log squared. So we would like to decrease that. So sample sort is a more practically used algorithm these days, but it uses Bitonic sort, so still useful to learn. And also Bitonic sort is kind of cute, so it's worth doing it anyway. Okay. So the high level, there are two main categories of algorithms that we're going to do in this class. So far, we have pretty much mostly done regular algorithms, which are algorithms that do the same amount of data or work on every processor. So for example, like Bitonic sort, we had n elements, and the comparisons are always fixed up front, and you can always split them according to like the hypercube, their distance 2 and the distance 4 and so on away. And the work is uniform across the processors. And other examples of regular algorithms that we did, matrix multiply, I guess, is regular. Yeah, you have like the n cubed operations that you need to do, and you can always split those up evenly across your processors. And shortly, maybe in a couple lectures, we're going to do distributed memory matrix multiply, but we did it in shared memory already, and you can already evenly split that. On the other hand, we have irregular algorithms like sample sort, which have variable amounts of work on every processor. So this is just an illustration. Regular is like these are your processors, and this is your work, and they're all evenish. Maybe it's +1 off or something like that. But however, in the irregular case, the work may vary on the processor, and the time that your algorithm take is bounded below by the longest running processor. So even if some other ones finish earlier, the whole algorithm is not finished until the longest one finishes. So in that case, P2 is the longest one. Yeah, and the goal of the regular algorithms is you try to make the pieces as even as possible, because if you have one really long piece, it doesn't matter if all your other pieces are very short, because you still have to wait for that one to finish. So the goal is you try to kind of like bound the biggest piece, and we kind of did that when we were doing parallel merge sort. Like we were cutting the merge, and we wanted to show something like the merge is not perfectly even, but it's a constant factor off of each other. So you can prove bounds like that. Okay. Another trick that we're going to do today is sometimes in distributed memory, you can trade computation for communication a little bit. So that means you do a little bit of local work, like you do some work on a smaller part of the input, much smaller than n ideally. And ideally that can help you to save communication. And the reason that you might want to do that is usually when you use parallel computing in practice, you're not really limited by the number of processors that you have. Like usually you have enough parallelism, you have enough compute. You want to mitigate, but communication is much slower than computation. So you want to minimize the communication cost, even, and then you would get closer to this ideal time, which is serial time divided by p. Like that's like the best case scenario in some sense, not counting for any communication or anything. That's just if you got perfect speed up on p processors, and usually you don't get that because of communication. Yeah. So, and the reasoning for this is because like we have these constants mu and tau, and mu is one is like one is the relative or computation cost, so the cost of doing one operation, but mu is like the cost of transferring one byte or one word, and that is greater than the cost of doing like an addition, for example. And even greater than that is tau, which is the latency required to start your communication up front. So even if you got, like if you had a serial algorithm, you're only in this part, you're just doing the computation, but when you have a parallel algorithm, sometimes you may need to do some communication, and you want to reduce that. Okay, so I'm going to recap Bitonic sort briefly. So this is an example of the sorting network. And if you remember, there's like two parts kind of the Bitonic sort. One is that you you have an unsorted sequence and you want to create a sequence where half of it is going up and half of it is going down. And that is this first part here. And the second part is once you have the sequence going up and down, then you want to make that into a one single sorted sequence. And that is the second part, where you keep calling Bitonic merge. And Bitonic merge is a recursive function. So like Bitonic merge of 4 calls Bitonic merge of 2, so on. So this is Bitonic merge of 2, Bitonic merge of 4, and then 2. And then this is Bitonic merge of, 2, 1. Yeah, 1, 2, and then 2 calls 1, and then 4 calls 2 calls 1. So that's where you get the log squared. And the computation time on P processors, if n is not equal to P, you see this pattern all the time, you do the local sort up front. So that's n over P. You have n over P elements on your processor. So it's n log n to sort the elements. So that's n over P times log n over P. And the second part is doing this exchange. So that is, the reasoning for this is that you have log squared P levels of this communication. And in each round, you do n over P because you need to, rather than doing like, normally if you had one element per processor, you would just do compare exchange of a single element. And instead, the second part, you do merge split, which is you have two sorted lists, you merge them, and then you just cut them in half in the middle part. So that is going to take time n over P because each list is size n over P. So it takes n over P time to merge them, and you have log squared rounds of this, or log squared P. And then in terms of communication time, it's just based on the rounds, pretty much. So you can think of this as like you have log squared P rounds, and each round takes tau plus mu n over P, because tau is the upfront cost of latency, and then you need to exchange n over P elements times mu, which is the bandwidth. Yes. Yes, thank you. Good, great question. Because it's like, so you have two parts, which is like the sum of Bitonic merge cost up to, let's just call this I, and this is up to log, right? So each of these rounds is clearly n over P. So you're just trying to count, oh, sorry, it's too small. Let me go over there. So you want to sum up the cost of, and each one of these is n over P in length, and you have log of them because like this is 1, or P here is 8, yes. So you have 1 and then 2 and then 1. This is 4 and 2 and 1. So this part is log, right? And then this part is, this is like up to log minus 1, basically. This is log P minus 1. And if you sum up, so this part is just log, so that is fine. But this part is summing up numbers like I up to log P minus 1 of I. This is the number of rounds in this part. Yeah, and this is log squared. Yeah, thank you. Is that all good? Yeah, so yeah, it's a good question because this second half, like this part is log, and that's after you got the up and down part. But getting to the up and down part requires log squared. Yeah, thank you. Cool. So yeah, so ideally you want to improve on that because log squared is not the lower bound, and so in terms of communication time, yeah, again we have log squared P, and then each round is just tau plus mu n over P. Yes.
Do we know that log P is the lower bound?
We know that we will get there in 1 minute. It's actually not the lower bound. The sorting lower bound is n log n. I guess, like I just mean on one processor, the sorting lower bound is n log n. So the parallel lower bound, or a parallel lower bound, could be like n log n, the whole thing divided by p. So yeah, well, is that exactly right? Because this is less than that. Like, that's n log n. Oh, yeah, because that would be like n over p times log n. So actually, the lower bound should be even smaller than that. Wait, that's not right.
Like isn't the n over p thing like because you sort n over p in each processor first?
Yes, this is like the first local part. But I'm saying if you sorted n elements, the lower bound in serial is n log n. And then the parallel, in parallel, like you can do p of those steps at once. So that would be n over p times log n. So I guess maybe this is greater than n over p times log n, because you cannot beat that serial lower bound at n over p times log n. Yes.
Are we looking at the work here?
Oh, yes, yes, thank you. Yeah, this is not the, sorry, this is not the total work. This is just the computation time. Yeah, okay. So that's it. Yeah. We're in one moment, we're going to do like weaker lower bounds for this. Thanks. All good so far? So yeah, how are we going to prove these lower bounds on computation and communication? We're going to bound computation by n and p, and we're going to bound communication by n and p and the computation constants tau and mu. So how would we prove these lower bounds? Well, we can start with computation, or we can start with communication, because maybe that's easier. Well, one thing that we can observe is everybody gets, let's say that everybody gets n over p elements up front. In the worst case, your n over p elements need to go somewhere else. Like let's say those don't belong to you in the end, and they have to go elsewhere. It doesn't matter where they go, it could all go to the same or all go somewhere different. But that is going to take you at least mu times n over p to send away. And same for everyone. So even if you all did it perfectly in parallel and there are no conflicts, it would still take mu n over p. Yeah. Okay. So like I said, starting lower bound is n log n. In the worst case, you have to ship everybody away that you have. So it's n over p. And then the average case is also not better, because in the average case, you have to ship this amount, which is n over p times 1 minus 1 over p, because this 1 minus 1 over p is like the fraction that is staying to you. And then 1 minus 1 over p is the fraction going elsewhere. So that's still like n over p. And then, so yeah, any sorting algorithm, therefore, like I said, it's at least mu n over p, because in the worst case, all of your elements have to go somewhere else. And there's communication, and then for computation, the lower bound is the like how many steps you have to do in serial divided by p, because in the best case, you do p of those steps in parallel. Okay. So Bitonic sort, I mean, we're probably not going to reach this lower bound, because this would kind of assume that magically we knew where everybody had to go up front, which is not going to happen, because that's the point of sorting. But we can try to get as close as possible to this communication lower bound. Okay. Yeah. So to recap, these are the lower bounds, and for Bitonic sort, we can repeat these bounds: local sorting part and Bitonic part. And then here, this is the Bitonic round. Like we don't pay for the local sort in the communication time. So this part goes away, but we just count for the communication the number of rounds times how much communication we had to do in every round. And that is log squared p off of this optimal lower bound. Okay, so it's not ideal to be log squared p off of this lower bound. And like I said, in the ideal case, you know upfront where every element is going, and also that everybody else is getting equal blocks from you, and also that the blocks happen to be in order as well, because it doesn't really matter for the communication time, but like if you knew upfront where every element was going, you would have to put them in the order, like first all the elements going to processor 0, and then second all the elements going to processor 1, and so on up to the end. So you have to do some local reshuffling, which counts in the computation time, but potentially less than local sorting. Okay. So one algorithm that kind of looks like this, well, yeah, one algorithm that kind of looks like this, which is where we're going to figure out where to ship all the elements, is quicksort. So in parallel, in distributed memory for quicksort, so for normally in quicksort, you pick a pivot and you split the elements to the left, like smaller on the left side of the pivot, bigger on the right side of the pivot, and then you recurse on the two halves. And that's a randomized thing, and you hope that ideally your pivot cuts the things approximately in half. But in reality, it may or may not be half, and it's like an expectation thing. And yeah, so in distributed memory, there's one issue, which is that you have to pick the pivot for the same for everybody. And the way you do that is somebody's going to have to pick the pivot, and then you're going to have to broadcast that pivot to everyone else. It is not going to work for everybody to pick their own pivots, because then how are you going to shuffle around the elements? So you pick the pivot, you broadcast that, and once everybody has the pivot, you partition your elements locally. And that is going to take n over p, because everybody has n over p elements. You rearrange the partitions, doing this kind of many-to-many all-to-all communication. So you pick one pivot, everybody has some elements to the right of the pivot and some elements to the left of the pivot. And here, orange is on the right, green is on the left, and we're going to put green elements on the lower half of the processors and orange elements on the higher half of the processors, like this. And then you split the processors, and then you continue to recurse. And this is, like we talked about MPI ComSplit when we were doing MPI. And ComSplit is used sometimes in these cases, which is you have these like lower half and upper half, and now you want to split them into separate communicators, and now you can continue to call your recursion. And at the end, the base case is when p is equal to 1, you do some local sorting, and then you come back up. Does that make sense? Yes.
So half the elements to go on one side and the other side, wouldn't that be exactly?
Yes. So this is like a randomized thing, and in expectation, we hope that there are n elements, or like we hope that the pivot splits the problems in half. So like it would be n over 2 in the ideal case, but in the very worst case, it would be n squared, because in the worst case, you could just pick like the min. You would just keep picking the min in each one, and then the length of that tree would be n squared. Or, sorry, the length of the tree is n, but then each level you have to do n work. So the total work would be n squared.
So like for the green and orange block, every single processor has like different data set, right?
Yes.
Yeah. Okay. So like wouldn't there be the case where like pivot just like maybe it happens at the very left?
It can happen.
So like certain processors like they don't have a pivot at all.
Yes. So then all the elements would be either to the right or the left of that. So for example, like here, let's say the pivot was here, like this whole thing would be green, and then you would need to push all the green elements, all of the elements from here onto one of these lower processors. Yeah. So that is one issue with quicksort, is that it's a randomized algorithm, and you can prove that it's good in expectation, which is like on average, if you average out over all the possible pivots, the most average one is in the middle. So on average, that's n work per level, because the partition is time n to do the reshuffling in serial. And then you have log n levels if you, in expectation, cut it exactly in half. And that's why quicksort is expected time n log n in serial. But of course, as you observed, it is unlikely that you always choose the midpoint. And so you may have some imbalance. And also in parallel, like both in serial and in parallel.
Like much better than parallel merge sort, because I remember like at least serial way, quicksort is only like I think it's only like a constant better than merge sort in like in expectation.
Is it a constant better in merge sort? Wouldn't it be a constant worse than merge sort?
I think it's better. like like in real life it performs better than merge sort.
Because the partition is faster than the merge.
Because I think like I think it probably might be to do with how we pick a pivot. Like it actually does manage to, like at least in implementation, it manages to perform faster.
But like in merge sort, the problem is cut exactly in half.
Yeah.
So in quicksort, the best you can do is you cut the problem
Because
exactly in half.
I remember like someone telling me like in competitive programming they will like a lot of cases like merge sort doesn't work. Like you have to use quicksort because it actually performs faster. I'm not really sure why though. Yeah, it goes up against what I would think.
Yeah, that's a good point. I don't know. I would think that it's because like it's not because of the problem splitting, because the best you can do is you split the problem exactly in half every time, like in terms of balancing and like merge sort is always log n levels, but quicksort is expected log n levels. But if you cut it unevenly, you may get more. So the only difference then is in quicksort each level does the partition, and in merge sort each level does the merge. And the merge you have to like do conditional checking, like you put the min in every time. But in quicksort you can like blindly move the elements in your partition. Maybe that's why. But is quicksort good in parallel? Actually, it's not bad in parallel, but you just run into this potential randomized worst case, which is if you keep cutting very imbalanced, then you would get like a very long tail in your serial part. Okay, and yeah, so to analyze this in expectation, there are log p divisions before you get to your local sorting, and the computation time is this is the local sort n over p times log n over p, and then this is the partition n over p times log p. There are log p levels of problem because you keep cutting the processors in half, and you hope that that also cuts the elements in half. And this thing is bigger than this thing, so it's bounded above by n log n over p. Communication time, you have log p rounds of cutting. Each one has to communicate n over p elements, so that's tau plus mu n over p. Yeah, and this could be worse so this depends on log p being the number of levels of your recursion, but if it's cut unevenly, then you may have at worst p levels of cutting, because in the worst case you get like one processor each time. Does that make sense? Yeah. So quicksort is a good candidate for parallel sorting, but the problem is, of course, that there's this randomization, so you may run into the bad cases. Yeah, I guess, yeah, so one way you could avoid this broadcast, though it doesn't really matter that much because it's a low order term in the whole thing, but if everybody uses the same random number generator, you could just you just generate the same random number on everyone, then you don't have to broadcast a pivot. And then, yeah, and those are repeating the lower bounds. Computation is n log n, the whole thing divided by p, and communication is mu n over p. So it's closer. If you remember, Bitonic sort was log squared p. This is log p. So it's getting closer to this lower bound, but it's randomized. Yeah. And in the best case, if you knew what the global median was upfront, then you would do a perfect job of cutting the elements in half. Yes. We're trying to see how close we can get to the lower bound. These are upper bounds, or these are expected upper bounds. Yeah, but the broadcasting is small relative to the rest of it because it's tau plus u, and you already have to pay mu n over p. question. Yeah, this is we're probably not going to reach this communication lower bound because that assumes that you know where to go up front and that everyone is evenly distributed, which is unlikely, but we can try. Okay, and we want to try to lower this log p part. Okay, does that make sense so far? So another algorithm, or yeah, so the main algorithm that I want to focus on today is called sample sort. And sample sort is it's kind of like quicksort in the sense that you pick pivots, but the high level idea is that rather than picking one pivot, you pick p pivots, because so like if you remember where this log p came from, it came from the fact that we split this processors in half every time. And so we had p processors up front, and there are log p levels if you always cut them in half. But there's no reason that we necessarily need to cut them in half every time. Like, why couldn't we have just cut them in p up front? And that's like how we would get the communication lower bound, is that if we knew up front where elements are going to all the p processors. So simple sort, rather than choosing one process, or rather than choosing one pivot, we're going to try to choose p pivots. And then that is going to allow us to not have to do this cutting into halves every time for the processors. So we're just going to try this. The first step is always that you sort locally. So you have to pay this always, n over p times log n over p. And then we're going to pick p minus 1 random samples globally. And that is going to take p log p because you're going to do them in a tree. Why isn't it just p? Anyway, it doesn't really matter, I guess, because this is still a low order term, but maybe this should be p. Like if you just picked one sample randomly, like if everybody generated a random number. Oh, it's p log p because you have to do the broadcast, I guess. Sorry, that's my bad. Yes. So if everybody chose one pivot, just that's kind of free, like you generate a random number or something, and then now everybody else needs to know the pivot that everybody else chose. And that's why this p log p is happening, because you do a all-to-all, or all gather.
Don't those normally have the mu and tau in them, the all-to-all?
Yes, here we are just doing the computation cost, I guess. We're doing the computation cost of everything that's not, oh, I guess so. Yeah, this should be tau plus mu, I guess, tau plus mu times p log p, because this is an all gather. Like all gather is every processor has something that's into every other processor, and it needs to show up on every other processor as well. So yeah, I think it's just not there because this is a low order term. So even if you have the communication constant, it's still less than the end shuffle, like the end partitioning, probably. But yes, in reality, this should include mu and tau. I'll fix it. Okay, so you pick the p random samples, and everybody needs to know the samples that everybody else chose. And then you split the local sequence into p segments given the samples. That's local computation, that's n over p. Like in this picture, everybody has their section. And then this part with the arrows is the all-to-all communication, which is everybody knows which section of their element is going to p0. Everybody knows which section of their elements is going to p1, so they need to all ship it to the right places. And then we need to locally merge the sequences, because once we have shipped the elements to the correct place, they're not in the right order, so you need to, but they are sorted, so you can just merge them. And the problem with this is that it doesn't solve the imbalance issue that we had previously, because you could pick worst case pivots, like all the elements are going to one processor. And so the worst case imbalance is up to omega n, like all the elements are going here. Does that make sense? Oh, just that in the worst case, that's saying like in the worst case, how many elements could any processor get? It's lower bounded by n. Lower imbalance is defined as like the max over the processors of how many elements are destined for that processor. Does that make sense? Yes.
I'm so kind of confused on why number 2 is P1. I thought broadcast was like
Oh, broadcasting is log p, but you have p of them to do. Like one way to do this is that every processor broadcasts its pivot to every other processor.
oh, okay.
Like, yeah, does that make sense? Yeah. So there is some issue here, but we can fix it. I guess the first step is, yeah, we're gonna fix this load imbalance. But the high level idea is good, which is that rather than picking one pivot, you choose p. Okay. In an ideal case, the issue was that we had this imbalance. In an ideal case, you would choose p minus 1 good splitters, where good means that you cut the elements approximately evenly across the processors. And then you would just do the same thing in the rest of it. The rest is the exact same thing. You figure out what is going where, you do the exchange, and then you locally merge them. And the definition of good splitter is that each processor should get at least this number, which is m over some constant times n over p. So everybody gets within a constant factor of the perfectly even distribution, which is n over p. And c is greater than 1, but it's small, something like ideally like 2. And also finding these good splitters should not be too expensive. It should be less than the highest cost of the rest of the thing, because then we don't want to blow up the overall complexity. Yes. It's a good question. You can do, there's a couple ways that you can do this. One is that like in MPI, you have all to all, or you have all to all v, in which you also pass in a vector. So in all to all, you say like, you give the data, and then you can also pass in a vector of how many elements in each one of these is going to each one of the processors. So like you pass in a vector of data of length n, and then you pass in another vector of length p, where the vector of length p is like the displacements, and that is saying like the elements are like 0, 5, 10, for example, and that's saying like 0 through 5 are going to processor 0, 5 through 10 are going to processor 1, and so on like that. You could also use prefix sums. So like after doing this partition in the p splitters, everybody knows how many elements are going where. And then so if you did it, so like everybody knows, for example, how many elements are going to processor 0. And so if you did a prefix sum on all those elements, that would tell you like in the output array where the elements are going from each processor. That make sense? Yeah. Yes.
Like when you're doing your receive call, don't you have to say like how many things you're receiving? That part.
Do you know that part? Each processor knows how many it's going to send to processor 0. So if you add them all up, that is the size of the buffer that processor 0 needs to make. And then the second problem is like, yeah, we know the total size, but how do you know like where is processor 1's element starting and where's processor 2's element starting? And to figure that out, you know how many elements are going to processor 0 from processor 0, you know how many elements are going from processor 1 to 0 and 2 to 0 and so on. So you do a prefix sum on those sizes, and then that's where you start writing.
So do you need like 2 rounds of communication? You need one where they're all saying like how many elements they're going to send to it, and then the next one where you actually send the elements?
You could do it in 2 rounds. You could also call, there's like all to all v in MPI that you can do it in one pass where you just also pass in the sizes. But that would also be smaller. Even if you did it in 2 rounds, the first round would be smaller than this one because that would be, you're just sending one element per each. So that's like the size, the communication cost of prefix sum is smaller than this. Make sense? Like you would, communication cost of prefix sum is like, well, for one, that's like 1 element per processor. So that's just log p. I guess log p times tau. but tau log p is less than tau p. Yeah, really good question. You could do it in two passes, and you don't even need to do the sum up front. You can just do the prefix sum because the last element in the prefix sum is the total size. So the total size, so like you could get a vector of size p. Everybody could get a vector of size p, which is corresponding to how many, like the start point of every source processor writing to you or sending you stuff. And then the last element is the total size of that buffer. So you allocate a buffer of that size, and then you use the prefix of vector to tell you where you start writing. Yeah, good. Or MPI already has the built-in like also all v, where v is variable size from everybody. Yeah, good point. Yes.
The local merge is like based on.
The local merge, we will get there in 1 second. The local merge is simply they're already sorted because we sorted locally up front.
Oh.
Yeah. So every processor is going to send a piece of its sorted list to every other processor, and now you need to merge those pieces into one larger sorted thing. Yeah, that makes sense. Yes, and we will do that in 1 moment. Yeah. So does this high-level direction make sense? Where we're going to go? Okay. Yeah. And ideally, we want this to be deterministic because we don't want to run into some randomized worst cases. And yeah, so how are we going to effectively merge these? We're going to merge them in a tournament. So suppose that we have these lists L1 through LP that we're trying to merge into one longer list L. And this is what we're going to do on every processor. And remember, like we just said, every processor has their locally sorted list. So they're just shipping like a sorted portion to the other processors. And the size of the sum of the lists, because we chose good splitters, is bounded by n over p, or order n over p. So you sum up over 1 up to p, you sum up the size of lists, and ideally that gives you something like order n over p, which is similar to an even split. We want to do this, if you remember, this is the bound that we gave on the previous slide, n over p times log p. N times log p, whole thing over p. And then this is ignoring the communication part, because this is saying, once we already have the elements on the processor, then how do we do this merge? And the way you do it is like through these local merges. So like L1 gets merged with L2, and then L3 gets merged with L4, and all the way down, LP minus 1 gets merged with LP. And then you merge those destination lists. So like the result of L1 and L2 gets merged with the result of L3 and L4, and all the way up like that. And there are p levels of this. Or there are log p this way, and p leaves in this tournament. Oh, sorry. No. Does this make sense? Yes.
So there are p levels of this.
Sorry, there are log. In this way, it's log p because there are p leaves, and then each one is 2 becomes 1. Yeah, so that's just maybe the merge. And so these can happen in parallel. Like this one has nothing to do with this one.
When we merge, they're not sorted. We just
These are already like L1, L2 are already sorted within themselves, and you want to make a sorted
L1 and
list.
L2 like are not sorted, right? With regards to each other.
They are not sorted with respect to each other. You're trying to make a new list. Like, so after this, you're going to get a list that's the size of L1 plus the size of L2, where the whole thing is sorted. But these are each internally sorted. It's kind of like the in merge sort, you know, you have the two halves, but and both are sorted, and you're trying to merge them into one big sorted thing. Yeah, it's like that. But this is like in merge sort, you only have 2 at once, but here you have p at once, and you don't want to do like you don't want to serialize the merge. One thing that you could do, which would be inefficient, is like you merge L2 and L1, or L1 and L2, and then after that you're like, okay, I have this output, now I'm going to merge in L3, I'm going to merge in L4, and so on. So that would be serialized.
Okay, so just make sure I get this right. Is the highest element in L1 is still lower than the smallest element in L2?
It could be. It doesn't have to be.
thought when you choose pivot, right, and you separate to L1, L2, all elements lower than that pivot, all elements higher.
Oh, I see. Sorry. That is confusing. Here, like, this is L1, this is L2, this is L3, this is L4.
Oh,
Yeah.
no.
Yeah, sorry. That is a good point. So, like, the merge is like, how do you have all these green ports, and then you're trying to merge them into one sorted thing that is like this big green thing. So that they could be overlapping and they don't have to be.
Motion the P versus parallel. They are on only one process.
You could do it in a tree, I guess. Like P1, like rather than shifting them all here, you could shift them like two of them, two of them, two of them. You're saying how do you do it in parallel on one processor? Yeah, if the one processor is serialized, then it would be, then you can't, because if you just had one thread. If you're trying to do it in parallel, then if you actually want to do this in parallel, like L1 and L2, for example, happen simultaneously with LP minus 1 and LP, then in this model where every processor is serial, then they would have to happen on different processors. So you could do like here, for example, you could P3 can send to P2, and then P1 can send to P0, and then you do merge here, and you do merge here. And then you ship them again. Like then you ship the sorted thing here, P2 to P0, and then you do a merge. So you do the tournament on the processors. Like each processor has some local list, and then like you follow this thing. So like P2 would send to P1, and then P would send to P minus 1, and then on P minus 1 you do the merge, or you do the local merge.
Another like
Yeah, that wouldn't. So that's like tau log p, I guess.
Yeah.
Yes, you can maybe get rid of that by saying it's already that's like a low order term in the overall thing, I guess, because the whole thing like you already have tau p, so you can afford tau log p. Yeah, it's a good question. Like, you maybe don't actually have to do this tournament merge if you're doing the all-to-all, because like in this, all the green parts after this, all the green parts end up on this one, and you're trying to merge like the different components, and maybe you can just merge them serially if they're already on one processor. But I think maybe the point of the tournament merge is just a higher level thing that like if you in general when you want to do parallel merges of different lists, that works. But if you do the local merge, then that would just be n over p. Like if you do it serially, the total size of those lists is n over p. So the algorithm, maybe the high level idea of the algorithm is there in the sense that like you keep one pointer for all of them, or like you keep one pointer for each list, and then if you were to do this in serial, you just keep popping them in off.
Like in the previous slide, it says like how to efficiently merge p sequences.
Mhm.
But in the next slide, it's actually doing the merging in like each. So like it's like merging the list in each sequence instead of merging the.
These are the p sequences, like L1 through
But
LP.
then if it's like the p sequences, I thought the p sequences make up like the entire list.
Yeah, you're trying to make them into one
So why
sorted
would
list.
it be upper bounded by O and
The size of the list is bounded. The size of the end list is bounded by n over p because the premise is that we chose these good pivots
So
such that
like
everybody
the-
gets.
So like for example, the green, yellow, orange, purple, like at the bottom,
Mm-hmm.
that's not the final list.
That is the final element in the list, but they have to get
So
sorted.
that has to be ON in total, right?
Adding all of these up, it has to be ON. And the premise is that we want to choose good pivots such that each of these is theta n over p. So we want to get good balance between the pieces. Yeah, so that's where we're getting this n over p, which is like the total size of this thing in the end is like n over p, or is order n over p.
So that's just a colored box. It's not the final entire list.
Each of these, like this is like L1, this is like L2.
Yeah, so like for example, the large green one is
This large green one is
that's
L.
L.
Yeah. So yeah, and then the main insight in this algorithm is how do you choose the good splitters to evenly distribute the elements. And the way that you do that is called oversampling. So at a high level, what's going to happen is that rather than choosing p, in the end we want p, but we choose approximately p squared overall. Like everybody elects p, and then those get the p squared. So everybody, there's p processors. Everybody chooses something like p. Actually, they choose p minus 1. And then you put those all together. So you have like p squared, and you sort those. And then you pick the p even points in that one. There's going to be a picture. Yeah. So basically the way it works is previously every processor picked one pivot, and then it did the partition according to that. Or sorry, every processor picked one pivot, and those p pivots got broadcasted everywhere else. Now, every processor is going to choose p pivots. We're going to collect all those p squared pivots. We're going to sort them, and then we're going to choose, in that p squared list, we're going to choose every p and try to make some argument that that is going to evenly partition the list. Okay, so this is an illustration. Suppose that we have 3 processors, and we have this initial distribution. They're approximately even sized. And so we look, the first step is to locally sort the elements. So it's just all the elements blue are sorted, green are sorted, and then pink are sorted. And then you choose even splitters. So you just choose we choose p minus 1 splitters, because afterwards, like everything is going to the end. And so these are just evenly spaced in the sorted list for everyone. So here we would choose 8 and 16. Here we would choose 9 and 20. Here we would choose 7 and 17. And these are just every 3 elements, because like you have 3, 4, 5, 6, 7, 8. So it doesn't perfectly divide 3, so you just approximately divide it by 3. And then you collect them all into this list. So every processor chose p minus 1 pivots. So this is p times p minus 1. And then you sort this thing. And now this is just all the pivots that are sorted. And now you kind of do the same trick. You choose evenly in this list of pivots. And you use those to partition the entire thing. So everything less than 8 is going in the first one. Everything between 8 and 17, at least 8 and less than 17 is going in the second one. And everything at least 17 is going in the last one. Make sense? Yeah. So the way this is going to go is that we're going to try to prove that choosing these gives us an even distribution, and also that this like small sorting is not going to contribute to the overall runtime much. And the reasoning for that is because this is p squared, and we hope that p squared is much less than n over p. It's probably true. Questions? Yeah. And Bitonic sort comes back because we had to sort this thing. Okay. So we're going to prove that we got an even load distribution through this splitting. And we want to prove that according to this scheme, every processor is going to receive at most 2n over p elements. And the way that you prove that is to make some argument about the elements between the, so these are called like logo splitters, which are the splitters that everybody chose. And the ones that got picked, these red ones here, are called global splitters. So those are like evenly spaced out in the local splitters. And the argument is basically that we want to make some argument that between two global splitters, there's at most p local splitters. And that makes sense because of the way we constructed them. And then from there, we argue, so like we're going to argue that there are p local splitters, at most p local splitters between any two global splitters. And then each of those local splitters is going to contribute at most n over p squared elements into the partition. So yeah, the number of local splitters between two global splitters is most p minus 1. Oh yeah, the number of local splitters contained in the elements in each processor is p minus 1. And then we're trying to say how many splitters came from each processor. And if you add them all up, there are only p minus 1 local splitters per processor. So how many of these local splitters came from that processor? Well, almost p minus 1. And then we can use that to bound how many elements came from that processor, because every local because of the way that we chose the local splitters, every processor has n over p elements, and we chose p local splitters. So in your local processor, the number of elements between any two local splitters is n over p squared. So that's why this n over p squared is here. And then we're trying to bound the number of elements that came from that, which comes, so this is every local splitter's contribution, and this is how many local splitters you got from this processor. How many local splitters was between. And then if you add them all up, so you sum them up over p, because you have two processors, then this thing comes out to be, you can split the sum. So that's s of I, n over p squared. This is just n over p squared. So this thing is clearly n over p, because it's just multiplying this by p. And then this thing, if you sum up s of, this thing can be pulled out like n over p squared. You pull that out here, and then the sum of this thing comes from here, which is p minus 1. So this is p minus 1 times n over p squared. Then this is p times n over p squared. This is at most 2n over p. Questions? Okay. Yeah, so that is how you choose good splitters, which approximately evenly distribute your elements. And how we did that was we oversampled, and then we sampled p from p squared. And that whole thing is deterministic. So you don't have minimization, and you don't run into this like expected issue. Okay. So what is the complexity of choosing these global splitters? We want to make sure that it didn't contribute too much into the overall runtime. And to know that, we need to bring back this bounds for Bitonic sort, because we're going to use Bitonic sort here to sort the p squared local splitters. Okay, so in this case, n is equal to something like p squared. And then you just plug in p squared for n into those bounds. So that is, for computation, p squared over p, this thing. So this is like p log p, and this is like p times log squared p. So that is p times log squared p is clearly bigger than p log p. And so that's this. In communication, you plug in p squared for n. This is mu p, this is log squared p. Yeah, and then, yeah. this is mu p. The whole thing is multiplied by log squared p. And then this is the complexity of the all gather is tau log p times mu p. Because you all gathered, there are p global splitters. So you just plug in p for n in the all gather. Okay. So in total, we want to add up, if you add up all of these steps, then you get the total time. So we just proved both the communication and computation time of the splitters and the computation time. This is the local sort, n over p times log n over p. The green part is choosing the splitters, p log squared p. And then this n over p log p is the merging part. And for the communication cost, this many communication, tau p times mu n over p, that's this orange thing. And this green thing is the communication cost of choosing the splitters. And if you add them up, this is n log n over p divided by p log squared p. Or sorry, n log this thing plus this thing, because this thing is bigger than that thing. And then similarly, in the order notation, you take the bigger things. So tau p plus mu. Yeah, so we drop this tau log squared p because we already had tau p. And then we have p log, we have mu, we pull out mu. This is n over p and p log squared p. Yeah, and that is optimal if n is at least, or n is greater than p squared log squared. Because then, so if you remember these lower bounds up there, computation time is n log n over p. So for computation time to be optimal, if this thing is bigger, then the whole thing is dominated by this, which is the lower bound. And yeah, and then you get that by just multiplying p on that other side. And then for communication, it's the same thing. You want mu n over p. You want this thing to be the biggest term. And so you just multiply by p. Questions? I think that's it, actually. So we have about 15 minutes. I don't know if it's worth starting something else. If there's anything that anybody wants to talk about, we can also do that. Or we could just end a bit early today and start again next time. Cool. Yeah, let me know if you have anything else that you want to mention. Thank you.